Sounds good. All right. Well, hello, everyone. Thank you for this opportunity to present on our datasets, CHIRPS, and CHIRTS. I am Shukla. I am a researcher at the Climate Hazard Center in the Department of Geography at UC Santa Barbara. Uh, and I mean, I'll talk a little bit more about this in a minute, but my research focuses on drought monitoring and drought forecasting using hydrologic model, remote sensing data, and so on, mainly to support food insecurity early warning in sub-Saharan Africa, Central America, and Central Asia. So with that, as you all know, the title of the presentation is Climate Hazard Center's Rainfall and Temperature Datasets. I should say that although there's a tagline here that everything you want to know about these valuable resources, I think it was a little presumptuous of me to assume that there are certainly some things that I may not know, but I'll try my best. So I just wanted to start by with a quick introduction to our research center. We are Climate Hazard Center at UC Santa Barbara. And here is just photos of some of our current and past members. Several of the researchers are based in Santa Barbara, but we also have a few regional scientists, like, for example, these gentlemen in Eastern Africa, gentlemen in West Africa and Central America, and those are our kind of representatives of our research center in different regions that are typically food insecure regions. And I should mention that the CHIRPS and CHIRTS dataset and this presentation is completely teamwork, and a lot of the members shown here have contributed to the data sets and this presentation. In general, Climate Hazard Center collaborates closely with the FuseNet Science team, Famine Early Warning System Network, and we collaborate with USGS, NASA, and NOAA colleagues. And overall goal of the center is to conduct research and provide data sets for actionable information by end users like FuseNet and other national and international agencies. So with that, this presentation will be a 5-part presentation. We'll start by just kind of talking briefly about the need for climate data, especially as it relates to health outcomes and the key challenges that exist in real-time monitoring of climate. And then part 2 will be how we are, through CHIRPS and CHIRTS, are tackling these challenges with climate monitoring. This part will also discuss the methods behind these data sets. In part 3, I will show some of the validation of these data sets. And in part 4, we'll highlight some of the key applications of these data sets, as well as data accessibility. So how can we access these data sets? And finally, I'll provide a key summary. So starting with the part 1, the why. And this is obviously something that you are all very well aware of, but climate, and in this case, referring to mainly rainfall and temperature, has an important impact on health outcomes, nutritional outcomes, and so on. So rainfall and temperature data are needed in real time and also long term. And by long term, I mean about at least for last 30 years and so, because they can be used to monitor climate hazards like droughts, floods, or heat waves. And why we monitor those climate hazards is because of their impact on nutritional outcomes and health outcomes. So if we want to kind of know, especially in advance, the possible impacts of climate hazards, we need to also have real-time and long-term precipitation and temperature data sets. Just as an example of two kind of key applications for how rainfall data and temperature data sets are used for nutritional or health outcomes. So in this example comes from a Southern Africa Regional Humanitarian Appeal report that was released in June of 2016. This was released following a major drought in Southern Africa, this part of Africa, and the drought was linked to a very strong El Nino event. And so on the left, what's shown here is the rainfall anomaly. Basically, in terms of rainfall, if a region was the driest on record or wettest on record. So wherever you are seeing fairly dark red or brown color, in those regions, in that particular season, the rainfall was driest on record. And I think the record in this case goes back to 30 to 40 years. So this map shows the severity of that drought event. And this map, along with several other indicators, it contributed to the kind of the description of the possible impact of the drought. And this was used to put together an appeal for funding to support emergency food assistance need. And on the right is basically estimate of the impacts of this food insecurity in terms of total funding that was required, in terms of number of people who might experience emergency food assistance and so on. And then looking at temperature, we can also use temperature, in this case, the maximum wet bulb globe temperature, to monitor heat stress. So in this example, we're looking at last week or so of May of 2024 and focusing mainly on Southeast Asia. Using our data sets, we can, for that particular part of the month, we were able to highlight the regions of Southeast Asia that were experiencing the hottest WBGT, the wet bulb globe temperature on record. And all of the places that you are seeing where there's a kind of hatch or positive sign, those are the regions where the temperature was hottest on record. So again, like this kind of availability of these kind of temperature data can allow for large scale monitoring of heat stress over the globe. So, those are two quick examples of how these temperature and rainfall data set can be used for supporting nutritional outcome analysis or humid heat stress. But what are the main challenges in having these real-time data sets is that we have seen a lot of variability in the station density across the globe. So the map on the left shows the location of rainfall data sets across the globe. And as you can see that there's a large part of Africa, parts of Asia, where the density, where you see the green color being very sparse. So this highlights a main challenge that the density of stations is very minimal in a lot of those places where population might be a little more at climate risk and more vulnerable. In addition to the spatial sparseness, these reports of the station data have also been decreasing over time. So the map on the right shows the number of station counts using 3 different data sets over time. So as you can see that maybe in 1980s, we were close to about 40 to 50K stations across the globe. Now we are down to close to 10K or so. And this is, again, a global representation. if we were making the same figure for, say, continent of Africa or a certain countries, we would see even a steeper decline. So both of these main challenges make it much harder to have a long-term, real-time, and consistent monitoring data set. So that leads us to the second part of the presentation, where we will highlight how using CHIRPS and CHIRTS, we are trying to tackle this main issue of sparse station data and decline in station data reports, and also highlight the methods behind both of those data sets. So I know this is a very busy slide. This slide represents the methodology behind our rainfall data set. But before getting into the details, I just wanted to kind of highlight 4 steps that are at the core of the methodology for CHIRPS and CHIRTS. And those 4 steps are include creation of a high resolution climatology. So the first step is that we use all of the available station data across the globe, plus some satellite data to put together basically a climatology, the mean field. So what is the mean rainfall over the globe? What is the mean temperature over the globe? And how variable spatially it is across the globe? We first try to get an estimate of that quantity for across the globe. So first we get a mean, high resolution mean. And the second step is to use the satellite data to get the temporal variability. So we convert generally the satellite data into an anomaly field. So we compare the satellite data related to its mean and get the variability across time. And then in the third step, we basically take the mean field, the climatology, which is the spatial high resolution variability, and apply the temporal variability on it, which gets us this type of estimate where we can, throughout the time, we have some estimate of rainfall or temperature, again, using the combination of the high resolution climatology and temporal anomaly. And then in the final step, we use the station data that are available to us to adjust our gridded field to make sure that in the places where we have enough stations, the bias between this data set, which is purely based on satellite, versus the station reports is very minimal. So this is basically a kind of a quick basics of the process behind both CHIRPS and CHIRTS, and it's fairly similar. And by doing this, we basically try to adjust for the lack of station data over time, because the temporal variability is coming from the satellite data as well. So even if you have missing stations, you can get some information from the satellite data. And because, at least in the past, there were a lot of stations available, we can use the historical station data to get a sense of the mean climatology and how it varies over the space. So this is the methodology for CHIRPS. We use something very similar for CHIRTS, which is temperature data. And I'm going to describe the CHIRTS methodology in 2 steps. First, I will describe how we generate the monthly temperature max values, and then how we go from monthly temperature max to daily temperature max. So again, a similar approach where we first start by putting together a climatology, the mean field. In this case, we are using CRU data, which is a very widely used grid data. We use the reanalysis from MERA2. We also use the other static factors like elevations, latitude and longitude to get the mean temperature field. We then, using the satellite data, we, again, same process. We create a variability anomaly over time using the satellite data. We do the same using station data too, and we merge them together to get basically a satellite and temperature-based anomaly that we can then apply on the mean field. So again, mean, temperature mean, plus the anomaly will get us absolute value of temperature. So we have three versions of the temperature data at monthly scale. One version is purely based on satellite. The second version is purely based on station. And the third version that has the S in the end, which stands for station, is based on satellite and station as well. So after getting the monthly Tmax value, we try to estimate daily Tmax value and T minimum value. And for this, we use the ERA5 reanalysis, which it's likely that a lot of you are familiar with. It is a European reanalysis data set, very widely used in a lot of research. But this data set provides temperature max at daily scale and temperature minimum. And what we basically do is that we apply the monthly temperature max on the daily temperature max data. So for example, we get the daily value of temperature for a grid cell from ERA5 and adjust the daily value so that the monthly Tmax value of that data set is similar to our CHIRTS MAC data set. And then since ERA5 data comes with temperature minimum, we kind of know the difference between the temperature max in any given place versus temperature minimum. We take that diurnal temperature range and apply that on the Tmax data to get the daily temperature minimum data as well. In addition to this data set, for availability of real-time temperature data, we are also working with ERA5 to generate a bias-corrected daily temperature data. So I just wanted to kind of highlight the difference between the mean temperature from ERA5, which is reanalysis, versus CHIRTS daily, which is based on station and satellite. And this basically for the month of January, this shows how different the monthly mean temperature are between both data sets. And you can see that in a lot of places, we see blue colors, meaning the ERA5 is a little colder than CHIRTS max daily values. In some cases, these differences is even higher. So what we do is that we apply a mean correction process that matches the mean of the ERA5 with the CHIRTS daily mean. And that helps us get the daily temperature data in real time because ERA5 does provide the daily temperature data in real time. So this is just an example that after bias correction, we get CHIRTS ERA5. And then if we compare the mean of CHIRTS ERA5 with CHIRTS daily, we get almost close to zero difference across the globe. So then after moving from the methodology, I thought we'll also show some ground truthing validation of these data sets. And I just wanted to kind of start by saying that especially for CHIRPS, the rainfall data set, the first paper came out in 2015. And since then, there have been hundreds of papers that have evaluated the rainfall data sets for different parts of the globe. So you can certainly find for your domain of interest, you can find papers that have verified CHIRPS for those particular domains. But here I will just highlight a few examples where we have done some validation of these both rainfall and temperature data set. But before I do that, I wanted to kind of highlight the value of high resolution, high spatial resolution. So this figure on the left, it shows the anomaly of temperature max based on CHIRPS max dataset. This dataset is available at 5 km by 5 km spatial resolution. And we compared that with the temperature anomaly based on CRU dataset, which is a very widely used dataset. It's based mostly on the station. And I think the resolution might be close to 50 km by 50 km. So you can see, we're representing the temperature max anomaly of the same month, but there is a substantial variability in the spatial anomalies in both cases. This is Ethiopia, Kenya, Somalia, particularly over Ethiopia and Western Highlands. You start to see, the differences because of the elevations, because of the land use, and so on. And you can basically represent a lot more spatial variability in a data set like CHIRTS, which is high resolution. This is just a validation of the CHIRTS Era 5 dataset, which we generate in real time, related to Era 5, which is again reanalysis. And in this case, we are comparing both CHIRTS Era 5 and Era 5 with a station in Zimbabwe. So what we find, just the kind of the big picture result is that if you look at the correlation between the station and CHIRTS Era 5 or station and Era 5, the correlation is fairly similar. It's about close to 1. But if we look at the bias, the difference between the mean, for example, then the Era 5 is much colder. It's about 1.45 degrees Celsius cooler than the station. Whereas the CHIRTS Era 5 that we generate in real time has a very small difference between the mean of the CHIRTS Era 5 and the station data. I should highlight that in this case, the blue line here is the kind of the moving average of the GSOT, which is the station data. Black line is CHIRTS Era 5, and gray line is Era 5. And you can see in general, the blue and the black lines are closer together, basically indicating that for this independent station, CHIRTS Era 5 that we generate in real time compares fairly well to the stations than Era 5, which is simply a reanalysis product. So with that, I also wanted to show some kind of a broad scale validation of the rainfall data set. And in this case, what we are showing is a correlation between CHIRPS 3 and other rainfall data set relative to a data set called RegM. This basically stands for rainfall estimates on a gridded network. So this is a data set that is basically based on stations. And we are comparing here the satellite-based rainfall product with this station-based product. And as you can see here, in general, CHIRP 3, this is North America, Australia, Europe, and so on. We see high correlation between both data sets. And in some cases, other data set like Persian, which comes from UC Irvine, we see lower correlation and so on. We can also, in relation to correlation, we can also look at the mean error between both data sets. So again, we're using the satellite-based precipitation estimates, comparing it with the station-based precipitation estimates. And as you can see here, in general, we see lighter color in case of CHIRP 3, which basically indicates lower values of error in CHIRP 3 related to other data sets, like even Persian data set or iMerge in some cases has higher error, much higher error than CHIRP 3. So again, this is another way of kind of providing a broad-based validation of this data set related to other estimates that are widely available and usable. Next, I also wanted to show some more comparison with stations. So in this case, we are comparing CHIRP3, which is our latest rainfall data set, and CHIRP2, which it was generated in 2015, but we are still continuing it. And by the end of this year, we are hoping to kind of discontinue CHIRP2. So what we are showing here is uh, a comparison of the standard deviations of both of these data set with the station data set. And we find that CHIRP3, the newest version of our data set, compares much better. It's very close to the 1-1 line when we are comparing it with the station, especially when it comes to the variability of the rainfall. And that we know was a major issue with CHIRPS 2, where we were unable to get some of the extreme events, extreme rainfall events, because we were not able to capture the variability as well. And this is just showing the uh, same variability, but for the precipitation events that are in 90 percentile, so extreme rain. So if we take the extreme rainfall events from the station versus from CHIRP 2 versus CHIRP 3, how well do they compare? And we find in general, CHIRP 3 still outperforms CHIRP 2. So this is a comparison done over a station in Ethiopia. We have done something similar over Morocco. And these are all stations that were not part of CHIRPS, generation process. And we again see the same finding that red dots here, which represents CHIRPS 3, is closer to the 1-1 line related to the previous version of CHIRPS, which is shown in blue. So this basically shows that we have been able to make further improvement in our rainfall data set, especially compared to independent stations. So now I'm just going to move on to the fourth part of the presentation. This will focus more on some key examples of application of this data set, and also highlight how we can access this data set. So I just wanted to firstly start by showing a graphics that shows that both CHIRPS and CHIRPS version 3 and CHIRPS version 2 data sets, they are widely used. This graphic shows the number of downloads that happen across the globe of this data set. Almost, users from almost all countries in the world are downloading our data sets. But it's kind of yeah, maybe mildly upsetting to see that we don't get as much download from Africa, where I think we do the best because related to other data sets. But we get a lot of downloads from Western Europe, US, India, and so on. We also keep track of the change in the download of our data sets with time. So, for example, right now in 2025, our daily data set gets downloaded by about 6,000 unique IPs each day. So we're very happy to see wide use of our data sets. Then I just wanted to highlight a few quick applications of the rainfall and temperature data set. So in this case, this example comes from East Africa. I think this report came in September of 2022, and this was highlighting the ongoing drought in Somalia at that time and the assessment of food security, insecurity in Somalia at that time. So this report comes from USAID. This is basically a tweet from then ambassador of USAID ambassador who was using CHIRPS rainfall data set to highlight the difference in the rainfall drought in 2022 season versus 2017 season, which was the previous worst drought year. And based on this kind of comparison, the USAID invested about 151 billion for funding in Somalia, and also, there was a appeal for emergency funding of about 885 million in that fiscal year. Obviously, USAID is no more, but FuseNet is working with Department of State. So we're hoping that we can still help with similar decisions for relief and food aid. This is another example. This is more recent, but some of you may already know that in Somalia this season, in October to December, Somalia and parts of Ethiopia and Kenya received very little rainfall, basically historically low rainfall, and that leads to a major drought event. So we were again using the rainfall data set. We put together a alert, which was a multi-partner event. A lot of the international agencies were on this alert, and they were using this rainfall data set as one of the evidence for the severity of drought. And then this was used to then identify the drought severity in different parts of Somalia. This became part of the spatial alert and so on. So again, like this highlights how this rainfall data set is being used on a routine basis to inform the severity of drought events and to help estimate the possible impacts on food insecurity. We also use both our rainfall data and temperature data routinely in our reports to CM4EW, which is Crop Monitor for Early Warning. This is again another kind of platform that provides kind of current state of food insecurity, crop conditions across the globe. So we provide input to that report using our rainfall and temperature data on a monthly basis. And then finally, I just wanted to highlight a experimental product that our group has put together, and it gets updated each few pentads, so every 5 days or so. But this experimental website shows it highlights the places around the world where the humid heat risk is fairly high right now. So this is based on the data from January 6th to January 20th, and it highlights all of the places where heat index is more than 90th percentile of their normal. This is still an experimental product. We definitely think that there will be improvement. And again, like if the audience wanted to use it and suggest any changes, improvement, we would definitely be happy to receive those. And this is, I just summarized a few different ways where you can get access to the data. I think the main place to kind of get more information about these data sets is our data website. So you can go on this link and read about all of our data sets, find citations, find other links where you can download data from. And I'm summarizing some of those links here. So you can certainly go and download the data set as you need. So with that, I just wanted to quickly summarize and say that CHIRPS and CHIRTS, they provide global, daily, and high-resolution monitoring, especially in places where ground stations are fairly sparse. CHIRPS and CHIRTS are routinely used to monitor climate hazards and also provide estimates of food insecurity and support food insecurity early warning. Both CHIRPS and CHIRTS are open access data sets. They are downloaded pretty frequently from around the world. The new version of Rainfall, the CHIRPS version 3, we find that to be better able to capture extreme events and rainfall variability than the previous version of CHIRPS. And the new CHIRTS Era 5 dataset that I mentioned, it is allowing us to better track in real time humidity, heat stress across the globe. So with that, this is just a list of all the references that are key for these data sets if anyone has interest. And yeah, and that's all. I just wanted to thank you all for your attention. Thank you to our main funders, which are FuseNet, USJ, US, and NASA. And I'll be happy to take any questions. Thanks very much.
Thank you so much, Shrad. I wanted to apologize to everyone for being late. I had a little bit of difficulty getting in, but I was supposed to have introduced Shrad, who is an amazing colleague and researcher who has been um, such a great resource as I, a social scientist, try and learn about how best to use charts and chirps. And Shrad is always down to provide a ton of data support and intellectual support and all sorts of things, emotional support when we kind of work. So, yes, so he's
Thank
such
you.
a gift to the field, and we're so
Thank
lucky
you.
to have him. And thank you so much for your time, Shrad. And I'm so sorry that I missed the intro. We have a bunch of questions,
Okay.
sorry, in the discussion over here, and
Hmm.
I can go through those. Um, uh,
Sounds good.
but anyone, I think you're okay if people want to raise their hands and I can kind of point towards them too and just help
Yeah,
organize this. But thank you, thank you, thank you. Can I start with one of the questions from the chat?
sure.
Okay, so this is a good old Jenna, a little self-deprecating. This is a bit of a basic question. What exactly is a reanalysis data set? Is it just
Yeah,
reanalysis of existing weather? We just don't talk about it like this in demography and social sciences. So can you explain to us what it means to be a reanalysis?
yeah. No, thanks very much for that question. And I think it's definitely so. First of all, I want to start by saying that reanalysis is extremely valuable, especially as I had mentioned before. Um, there is a general lack of station data across the globe. And reanalysis is basically a mix of model simulations. So, like you might generate simulations of rainfall, soil moisture, temperature, and all that using a model. Uh, and model simulations are basically bias corrected with the stations where they are available. So it's basically a mix of, and reanalysis like NR5 also use satellite. So basically, it's a mix of model simulations uh, corrected using stations data where it's available and using satellite data again where it's available. The benefit of reanalysis, at least two benefits that I would want to mention, is that reanalysis generally has low latency. Some of the reanalysis from NASA have maybe 2 or 3 weeks of latency, but ERA5 has about 3 to 5 days of latency, meaning you can go today and find data of last 2 or 3 days ago. So that's a huge benefit, especially for real-time monitoring. And also, a lot of these reanalysis, they are useful as basically kind of a starting point for weather forecast, for seasonal climate forecast. So because those all of those forecasts are model based and they have to start with the current state of the global climate, the reanalysis provides that current state. So for both of those purposes, reanalysis is a critical resource. Hopefully that makes sense.
Thanks. Thank you, Shrad. Okay, another question from Georgina.
Thank you.
Doesn't he Gamayel? Sorry, Georgina.
That's okay.
With the new CHIRTS Era 5 dataset, how does the data now extend beyond the 2016 data? Can you just tell us really quickly
Yeah,
what time periods are covered, if you roughly?
yeah, yeah,
Um,
yeah, yeah.
and then also another part of Georgina's question is around how to incorporate some of the work that they're doing she says she works with the Tanzania Meteorological Authority, and we are digitizing old station data to update temperature and rainfall normals. What would be the process to incorporate this extra station data into CHIRTS and CHIRPS? So time
Yeah.
period, then
Yes. Yeah,
process of
yeah,
station data, specifically Tanzania, but overall.
yeah. No, thank you again for that question. So uh, it's a little, I realize it's a little confusing, but for temperature, I mentioned two data sets, CHIRTS and CHIRTS ERA 5. The CHIRTS data set is purely based on satellite and station. And that data set is monthly and daily as well. But that data set ends in 2016. It covers majority of the globe at 5 kilometer by 5 kilometer resolution, but it ends in 2016. So after 2016, uh, in order to kind of complement the post 2016 period, we started to leverage ERA 5 reanalysis data. And what we basically do is we take the ERA 5 reanalysis data, interpolate it to the same resolution as CHIRTS data, and then we apply a bias correction. So you may remember that I was showing a slide that was highlighting the difference in the mean of CHIRTS versus ERA 5, and you were seeing that ERA 5 was much colder. And another slide which was showing the difference between CHIRTS ERA 5 and CHIRTS. And that was after this correction of bias. So post 2016, we are making use of ERA 5 data, interpolating it and bias correcting it to get us temperature data at a very low latency. So I think as of now, we are generating near present temperature data. So you can go on our website and get temperature data from 5 days ago. We have also kind of reconstructed CHIRTS ERA 5 to go back to all the way to 1981. So you can certainly download CHIRTS ERA 5 since 1981 until now. In terms of temperature data over Tanzania, we always welcome any station data that is available to us. The process would be to kind of get in touch with us, and what would be most beneficial is to get a relatively longer time period of the data in the past. So like say if you have the Tanzania data for last 20 years or so, that can help us kind of ingest that data into CHIRTS. In some cases, I will just quickly mention that in some cases we work with the Met agencies in Africa, where we empower the Met agency to ingest their own station data into our gridded data, because there are places where we're not necessarily allowed to access the station data, but we can work with the Met agency so that they can ingest their station data into our gridded data product without having to transfer any data to us. So definitely something we do, and definitely please feel free to reach out to us with any additional station data that you may have. Thank you.
Thank you.
Thanks.
Okay. Are you doing okay, Shrad? You ready for some more?
Yeah,
Okay.
it's all good.
This is kind of combining a few questions. In the past, I know for my own work and kind of thinking about what Deborah asked, also in the chat, does CHIRTS or CHIRPS do better in certain settings? Like I've had people say CHIRPS is not good for high rainfall zones, or it's only good at capturing places where there's very low rainfall, but it still can't capture no rainfall days, or those kinds of questions around
Yeah.
does it work well in all places, or are there specific agroecological zones where it works better? Kind of the same thing with urban and rural space.
Hmm.
Like, do you have insight into?
Yeah. Yeah. No, again, that's a very good question. So I should say that the the criticism that Kat you shared applied more to the previous version of CHIRPS, CHIRPS version 2, that had a known issue with capturing uh, the full variability of rainfall and also extreme events. So, for example, the way the methodology of the CHIRPS 2 came about, if if we were focusing on very dry regions where the rainfall in certain months is generally closer to zero, the CHIRPS version 2 would not be able to capture extreme events. Like we all know that in the last few years, there have been some major, rainfall events in the regions that are generally very dry. So like we can think about what happened in Libya, for example, a few years ago. There's also like, there was a rainfall event in, I think even Death Valley a few years ago. So CHIRPS version 2 was not very good at capturing those events. CHIRPS version 3, we have improved upon that. And which is why I was showing some comparisons of CHIRPS version 2, CHIRPS version 3 with independent station dataset. And we are finding that CHIRPS version 3 is better able to capture that variability. So extreme events, like the high end and also low end of rainfall. Because these data sets are based on a combination of station and satellite, uh, they will definitely, in general, perform poorly where, or relatively poorly, where station data are minimal or non-existent. So, frankly, in some cases, if we are not ingesting station data, it's not necessarily because there is no data there. Often it is the case that we just do not get the report. We basically the data is there, but we cannot access it. It's not available to us. So in those places where we have limited station density, I would expect our rainfall data set to do relatively worse than the regions where we have high station density. Uh, we have compared our data sets with data sets in, say, US, where we have generally higher station density, and CHIRPS 3 definitely tends to do better related to CHIRPS 2. Is
Okay.
that, yeah, go
That's,
ahead.
and then there's a couple follow-up questions. Um, should we be somehow including some measure of quality then or station data intensity in our modeling or as we select which countries or areas to focus on? And
Yeah.
also, should we this is my ack. Should we be redoing our analyses that we did with CHIRTS 2 with CHIRTS 3? Like, can we,
CHIRPS, yeah, the
or
P, yeah,
is my science garbage, is what I'm
yeah.
asking.
Well, so we have done a lot of comparison between CHIRPS version 2 and 3, and correlation wise, at least at monthly scale, the correlation is very high between both data sets. But the means is different. Uh, if you compare only the extreme events, that is different because CHIRPS 3 is better able to capture extreme events. Uh, what I would highly recommend that if you are starting an analysis now, I would certainly switch to CHIRPS 3 uh, because it is a improved data. Uh, and secondly, uh, CHIRPS 2 we will stop producing it at the end of this year. The another kind of improvement with CHIRPS 3 is also that we were able to get higher number of stations in CHIRPS 3 than we did in CHIRPS 2. In one of the early figures that I showed, there was a time series showing the number of station reports used in CHIRPS 2 versus CHIRPS 3. Uh, if we can go back to this time series, that shows that CHIRPS 3's reports over time, they were fairly stable, a lot more stable than CHIRPS version 2 was. So we basically are able to better maintain that station density over time with CHIRPS 3 than we did with CHIRPS 2, which will be very helpful.
Okay. Um,
Hi, Laura.
Bye, Lori. So yeah, this question about potential level of error. Is there any way for you all to produce some measure of confidence
Yeah, yeah,
or,
yeah,
you
yeah,
know, something that gives us some idea?
yes,
I think um
yeah,
for social scientists to understand that generating climate data is a science is hard
mhm,
for us. Like we like to think, and here's the rainfall data for 2008. It's never going to change. And so the
yeah,
idea that it continues to change,
yeah,
you all become more. expert at doing this or new data emerges or whatever is just something we're learning. So are there ways to think?
Yeah,
And also, just Kat, just to pop in. Hi, everybody. This is Deborah. I think that just, and hi, Shred, like when we produce a statistic for a region that comes out of survey data, for example, it would have error properties. Like we would generate for
yeah,
a point
yeah, yeah.
estimate, have standard errors,
Sure.
something like that. So I just, and not all data quality measures are alike, but I just, to Kat's point, I think social scientists, when using these data, feel more comfortable if they have a sense of the quality of the data
Yeah,
set. And I think when we use spatial data in particular, it's not really clear what those measures should look like. And so it's important to help sort of collectively think about those. Anyhow, I just wanted to add that
yeah,
before you
yeah,
answer
yeah.
for your thoughts.
No, it's definitely a great feedback, and I agree that we should provide some kind of error flag or confidence label, which we don't. And frankly, uh, the, some sort of error flag is generally common with other data sets. So, for example, if you're looking at vegetation data from satellite or soil moisture data set, it comes with many flags, flags related to cloud coverage, flags related to other type of uncertainty. So yes, we should definitely think about uh, adding another layer of error or uncertainty associated with our data. Uh, in a, I was going to say that yeah, I think I saw a question about the spatial resolution.
Yeah.
Uh, the the estimate that we provide for rainfall is average over 5 kilometer by 5 kilometer. So assuming that it is accurate for say a given point in that 5 kilometer, that's not fair. Uh, in general, with any of these data sets, aggregated value will have more confidence. So, for example, if we were looking at a watershed, if we were looking at a, again, watershed bigger than 5 kilometer by 5 kilometer, there are a lot of watershed that are smaller than that. Then at aggregate level, we would feel more confidence. And I should also mention that we have been using the rainfall data set for a lot of crop yield modeling, right? So we do compare the interannual variability of rainfall with the yield reports that come from Ministry of Agriculture. So those are purely independent data set. No, there's nothing nothing in common. But you still get depending on the data quality of the yield data, we get higher correlation in number of cases. So that shows that uh, at least at a broad scale, these data sets are representing something that's closer to the truth. I want to just say finally that all of the rainfall data sets, I think a fair term for all of them is estimate. So whatever we are doing is to get an estimate. There's no such thing as a true rainfall. If we can cover the entire planet with rain gauges, we would get different values at rain gauges depending on so many different things. So we're not getting to the truth of how much rain uh, occurred. We are just provided our best estimate using station, using satellite, using simulations.
We have just 3 more minutes. I'll ask a last question unless anyone
Okay.
else has one. But um, do you think then, kind of given all of that, that these are best used as sort of comparative measures, or should we be saying things like 6 millimeters of rainfall increases your risk of heart disease,
Mm,
whatever?
mm,
Or should we say more or less rainfall? Like, is it
mm.
more than,
Yeah,
what I'm getting at?
yeah. No, I think and obviously, Kat, your own research has used these data sets over time and found correspondence between, say, drought and malnutrition and so on. I think in general, it is a it would be fairer to use some kind of normalized threshold. So like not focusing on 6 millimeter, but focusing more on lower than 20 percentile rainfall. I think that would be a fairer thing to do. And also similarly for extreme events too, like when we say for any, extreme rainfall event that CHIRPS reported 200 millimeter of rainfall or whatever the number is, that isn't really a accurate estimate, right? Again, especially in extreme rainfall events, a very small, space might actually receive a lot more rainfall than CHIRPS can ever record. So I think to the extent possible, some kind of relative threshold normalized related to distribution would make more sense.
Okay.
I know that for some, say, temperature-related outcome, there are absolute values of temperature that are used. And I understand that. I mean, there are some, perhaps even medical reason to use those absolute thresholds. Yeah, Kev, please go ahead.
That's great. Thank you so much we're at time, I think. So, that's super helpful, Shrad. Thank you so much. And you don't mind if people reach out
Oh,
for
no, please, please.
follow-up.
Yeah,
Okay.
yeah, definitely.
Thank you.
Yeah, please email us. And thank you again for the opportunity and all the questions. I really
Thank you
appreciate it.
for all the work you do. I know
Thank you.
how hard you all work to make this data available to all of us. So thank you, thank you.
Well, thank you very much, everyone.
Yeah, thank you,
Bye,
Shrad.
everyone.
Thank you, Shrad.
Thank you.
Bye.